We tend to picture the ancient world as a place of brute labor, endless lines of men straining under the sun, dragging impossibly large stones inch by inch, building monuments only through raw muscle and blind persistence. That image has survived for centuries, reinforced by textbooks and artistic imagination, but it is incomplete. And as we peel back the layers of engineering history, we discover something radically different, a world where ingenuity mattered far more than sheer strength, where mechanical intelligence replaced wasted effort, and where a handful of engineers changed what entire civilizations could build. Nothing captures that shift more clearly than the Greco-Roman crane, a machine so deceptively simple, yet so mechanically elegant that it transformed the scale of ancient architecture. And what makes it truly astonishing is not that it worked, but how well it worked. Long before electricity, hydraulics, or industrial steel, ancient engineers unlocked a principle that still governs our machines today: mechanical advantage. The first clues appear in the late 6th century BC, carved into the limestone blocks of ancient Greek temples. These stones bear a strange signature: small, precise cuttings on their upper faces, impossible to explain by dragging alone. They look almost like handholds for invisible fingers, the kind of grip a lifting device would need. And indeed, that is exactly what they are. These markings show where lifting tongs or Lewis bolts once clamped the stones so they could be raised vertically, not slid horizontally. This wasn't an incremental improvement, it was a philosophical revolution. Instead of forcing men to fight gravity, Greek engineers began partnering with it, redistributing force, bending it, multiplying it. They created systems of pulleys that turned one person into 3, or 10, or 20. With each refinement, they demonstrated a truth that modern engineering students learn on day one. You don't need more strength, you need smarter leverage. But it was the Romans who turned this principle into empire-building power. Their simplest machine, the trispastos, looks almost laughably modest: a rope, a beam, and a set of pulleys offering a 3-to-1 advantage. Yet this humble tool allowed a single worker to lift 150 kilograms, 330 pounds, with surprising ease. One person now matched the work of 3, but when the Romans scaled it into the polyspastos, the numbers became staggering. Fitted with a large wooden treadwheel, a structure so big that men walked inside it like human-powered hamsters, the polyspastos could lift 6,000 kilograms, or more than 13,000 pounds. And not in theory, but in practice, at construction sites across the empire. To appreciate what that means, compare it to the Egyptians' traditional method. Dragging a 2.5-ton block on sledges required roughly 50 men. A Roman polyspastos, by contrast, could achieve the same lifting work with a fraction of the workforce. On a per-person basis, it was 60 times more efficient. Far from being crude, these cranes were marvels of precision craftsmanship. Archaeological evidence shows the Romans used bronze bearings polished to near-mirror smoothness, wooden gears cut with tight tolerances, and mathematically determined rope ratios that would not look out of place in a modern engineering textbook. They understood load distribution, stress concentration, and dynamic forces with a sophistication that challenges the idea of ancient primitiveness. Ancient construction sites must have been breathtaking to witness. Envision 4 men inside a giant treadwheel, walking in unison, their footsteps producing a rhythmic wooden thunder. As the wheel rotated, the rope wound upward, pulling massive stone blocks into the air as if defying the very nature of weight. Below, engineers monitored angles, pulley alignment, and anchor points. Their tools weren't computers, but geometry, experience, and absolute trust in physics. There was no electricity, no steel cables, no diesel engines, and yet the system worked flawlessly, day after day, for centuries. Not because it relied on brute force, but because it was optimized. Every component, material choice, and motion had been refined through generations of experimentation. And that refinement is what modern observers often overlook. The ancient world was not static. It was a laboratory, open air, large-scale, multi-generational. When a crane collapsed, lessons were learned. When a ratio proved inefficient, it was replaced. Over time, these machines became robust, standardized, and widely understood. They allowed the Romans to erect structures whose size and ambition remain unmatched. The Colosseum, the aqueducts, the Pantheon's towering facade. Without cranes, these monuments simply could not exist. But perhaps the most humbling demonstration of this ancient genius is not found in ruins, but in something you can build yourself. With nothing more than 3 hardware store pulleys, 6 meters of nylon rope, 2 anchors, and a modest test weight, you can recreate the exact same compound tackle the Romans used. Loop the rope through the pulleys in the proper sequence, fixed, moving, and suddenly a 40-kilogram mass rises as if it weighs 10. Your hands feel the same mechanical advantage that shaped marble cities. You experience the same physics that flowed through the minds of engineers 2,000 years ago. And this is where the lesson of the Greco-Roman crane becomes more than historical curiosity. It becomes a mirror held up to our modern world. We surround ourselves with devices that promise effortlessness but fail the moment the power grid flickers. We mistake complexity for progress and electricity for intelligence. Yet the oldest, most enduring technologies were built on principles that do not need charging, updating, or replacing. They endure because the forces they harness, gravity, tension, leverage, are constants of the universe. When the lights go out, the crane still works. And that is why studying it is not nostalgia. It is preparation. It is understanding how the world behaves when stripped of its comforts. It is a reminder that the strongest structures and most resilient systems do not depend on fragility, but on mastery of fundamental forces. The Greco-Roman crane was not just a machine. It was a declaration. Human strength is limited. Human ingenuity is not. We take water for granted. We expect it to obey gravity, to flow downward along the path of least resistance, to collect meekly in low places. Yet, over 2,000 years ago, ancient engineers challenged that assumption and built a device that forced water to rise against its nature. No engines, no pumps, no electricity. Just geometry, motion, and a profound understanding of how fluids behave. This device, the Archimedes screw, stands as one of the most elegant pieces of technology ever conceived. The fact that it is still used today, in both ancient irrigation fields and modern hydroelectric plants, is not a sign of nostalgia. It is a testament to how deeply it mastered the physics of force and flow. The core idea is almost deceptively simple. Place a helical screw inside a hollow tube, incline it at a specific angle, and rotate it steadily. Water enters the lower end, becomes trapped in pockets formed by the threads, and is carried upward as the screw turns. That's it. A child could draw it. But the principles behind why it works so reliably for centuries are anything but trivial. The screw likely originated around the 3rd century BC, traditionally attributed to Archimedes during his time in Egypt. Whether he invented it personally or adapted an earlier design remains debated. But what's certain is that the device transformed agriculture and engineering across the ancient Mediterranean. It allowed farmers to irrigate uphill, miners to drain flooded tunnels, and builders to move not only clean water but thick mud, silt, and even small stones, materials that would clog most modern pumps in seconds. Archaeological evidence shows that variations of the screw appeared in multiple civilizations. The Egyptians crafted precision versions using bronze, a material chosen not for ornament, but for its smooth, low-friction surface that reduced wear. The Romans, ever the empire-scale optimizers, enlarged the design dramatically. Their screws spanned several meters, rotating on wooden axles reinforced with iron collars. These massive installations could drain entire marshes or feed aqueducts that cut through arid terrain. Unlike many ancient machines, the Archimedes screw wasn't a tool of privilege or myth. It was a workhorse, a technology that shaped daily life. When we imagine ancient agriculture, we picture oxen and hand-carried buckets. But in reality, Vast landscapes were transformed through systematically arranged screws lifting water from rivers into fields. Each turn of the crank represented a form of automatic labor, multiplying human effort without burning fuel or exhausting animals. Its angle, a detail easily overlooked, was the key to performance. Through centuries of trial and observation, ancient engineers discovered that the optimal incline sat between 30 degrees and 40 degrees, too shallow, and the screw moved water inefficiently, too steep, and gravity defeated its upward pockets. At the optimal range, the device achieved around 30% energy efficiency, modest compared to modern electric pumps, but astonishingly reliable. Nothing broke. Nothing burned out. It could run constantly, day and night, without supervision. And that reliability is what sets it apart. Modern machines depend on seals, bearings, lubricants, and precisely machined metals. A single failure point can halt the entire system, but the Archimedes screw has no seals to rupture and virtually nothing to maintain. Its only requirement is rotation provided by humans, animals, water wheels, or windmills, depending on the region and era. Imagine the sights and sounds of such a machine working on an ancient riverbank. A wooden frame, sun-bleached and bound by iron straps, the rhythmic creak of a crankshaft, water glinting as it spirals upward, defying the slope of the hill, farmers guiding the flow into terraced channels where crops drank greedily. In the distance, the river continued its eternal downward course, unaware that human ingenuity had carved a new rule into its behavior. But the story of this machine doesn't end in antiquity. In a twist no ancient engineer could have predicted, we now use the Archimedes screw in reverse. Instead of forcing water upward, we allow water to descend naturally through the spiral, turning the screw like a turbine. The result? Clean electricity generated at low-head installation sites where the drop in water height is too small for traditional hydroelectric methods. It's a perfect example of technological reuse across millennia. The same spiral that once lifted water for Babylonian gardens now powers rural communities in Europe and Asia. It is especially valued for one unexpected reason: fish safety. Traditional turbines shred aquatic life. Archimedes screws, by contrast, move water gently, allowing fish to pass through unharmed. Ancient technology solutions meeting modern environmental priorities, a bridge across time. When we study surviving archaeological screws at Pompeii, we find something surprising: standardization. Multiple screws share identical dimensions, thread counts, and angles, evidence that the Romans had established engineering specifications long before industrial manufacturing existed. This level of uniformity suggests workshops, apprenticeships, and a culture of knowledge transfer. Someone wasn't just building these machines, they were teaching them. And that leads to a deeper realization. Ancient engineers were not guessing, they were experimenting, adjusting parameters, iterating, learning from failures. Through trial and refinement, they discovered truths about hydraulics that we validate today with equations and simulations. Their tools were simple, but their reasoning was rigorous. They built prototypes not in CAD software, but in the real world, at full scale. Consider what this means for us. In an age defined by electronic dependence, we often assume that progress equals complexity. But the Archimedes screw reminds us that the most resilient technologies are those that align with physical laws, not those that fight against them. When electricity fails, pumps stop, sensors die, control systems collapse, but a screw, a crank, and flowing water continue working unaffected. It forces us to confront an uncomfortable truth. Our ancestors may have understood sustainability more deeply than we do. They worked with nature, not against it. Their machines didn't last decades, they lasted millennia. They required no power grid, no mining of rare earth metals, no global supply chain. They relied on craft, geometry, and materials that the earth itself could replenish. And perhaps that is why the Archimedes screw continues to exert such fascination. Not because it is ancient, but because it is timeless. It is engineering stripped to its essence, form, motion, function, a spiral that reshaped civilizations, powered farms, drained swamps, and irrigated wonders, a machine that made water climb. And in doing so, taught humanity a lesson we are only now beginning to relearn. The most reliable technology is often the simplest, and often the oldest. We build our world out of materials we assume are strong: steel beams, reinforced concrete, high-grade composites. Yet, beneath their gleaming surfaces is a quiet truth architects rarely admit. Modern construction begins to decay almost from the moment it is completed. Cracks form, rebar corrodes, saltwater intrudes. Maintenance becomes a constant battle against time. And then, standing on a desolate Roman pier, battered for 2,000 years by relentless waves, you face a paradox. Their concrete is getting stronger. Ours is getting weaker. The Romans discovered a material that defied entropy, a concrete that didn't simply resist damage but actively healed itself. A material science breakthrough we're only now beginning to understand. And it wasn't the product of industrial chemistry or laboratory precision. It was the result of observation, geology, and a relationship with natural materials far deeper than what our modern supply chains allow. We often picture Roman engineering through their arches, aqueducts, and domes, but their greatest invention may not be visible at all. It lies inside their walls, foundations, breakwaters, and harbors a matrix of stone, lime, and volcanic ash that refuses to die. The secret begins at Mount Vesuvius. Long before it destroyed Pompeii, the volcano gifted the Romans a material called pozzolana, a mixture of volcanic ash and mineral-rich fragments unlike anything else in Europe. When mixed with lime and aggregate, it triggered chemical reactions that rewrote the rules of construction. Where modern Portland cement forms a rigid but vulnerable structure, Roman concrete remained chemically alive. Its secret weapon? Lime-class small, unmixed pockets of quicklime scattered throughout the mixture. Modern engineers once saw these as imperfections. Today we realize they were the key to the concrete's longevity. When seawater infiltrated a tiny crack in a Roman structure, an event that spells disaster for modern concrete, something remarkable happened. The water dissolved some of the lime clasts, creating a highly alkaline solution that reacted with volcanic minerals. The reaction produced new crystals, primarily aluminum tobermorite, a rare mineral that grows inside the crack and seals it from the inside out. Imagine concrete that heals like bone. That's not science fiction. That's Rome. Researchers have examined 2,000-year-old harbor concrete and found a dense network of interlocking crystals so tightly bonded that the material is stronger today than when it was first poured. And this was not luck. The Romans engineered multiple recipes depending on the job. Pumice-based lightweight concrete for massive domes like the Pantheon. Volcanic ash concrete for underwater foundations. Basalt-heavy mixes for military fortifications. Different aggregate gradients for seismic resistance. This was not primitive construction. It was material science centuries ahead of its time. To understand just how far ahead, picture a storm battering a Roman harbor. Saltwater hammers the seawall, waves break through gaps, and cracks form deep inside the structure. In modern concrete, those cracks would expand, rebar would rust, and the entire section would eventually need replacement. But in Roman concrete, those cracks become triggers, opportunities for the material to strengthen itself. As seawater seeps in, it activates the healing cycle. New minerals blossom inside microscopic crevices, stitching the structure back together. What should be the beginning of decay becomes the start of regeneration. Standing at the ancient port of Caesarea or Pozzuoli, you can touch blocks that have endured 10,000 storms. Their surface is rough, pitted, alive with crystal formations. When you tap them lightly, they sound solid, almost metallic. They are not monuments, they are survivors. Modern engineers have tried to replicate this recipe, but the results are elusive. The Romans didn't leave a single uniform formula. Their materials varied regionally, sourced from different volcanic landscapes. Each mixture had its own mineral fingerprint, its own internal ecosystem. Recreating it requires more than chemistry, it requires understanding how ancient builders and quarry workers intuitively selected and combined ingredients. But Roman genius didn't stop at concrete. Their mastery of materials extended into how they used them. They built with time, not against it. They planned for structures to interact with their environment, not resist it stubbornly. Nowhere is this clearer than in their approach to domes. In the Pantheon, the world's largest unreinforced concrete dome, materials are layered intelligently. Dense aggregate at the base for weight, lighter pumice near the oculus to reduce stress, gradual transitions that distribute load perfectly. No steel, no scaffolding left inside, no collapse in 1,900 years. Beside that triumph, our modern skyscrapers expected to last 50 to 100 years appear more disposable than eternal. But concrete isn't the only Roman insight into manipulating forces. While their concrete mastered chemistry, the Egyptians mastered friction, and the next great breakthrough came from a place we least expect. For centuries, we imagined pyramid builders dragging stones across dry sand, struggling against impossible resistance. But a single painting in the tomb of Jehu-Tihotep shows a man pouring water in front of a sledge. For decades, scholars assumed it was symbolic. Then physicists tested it. The result? The right amount of water reduces friction by up to 50%. Why? Because moisture forms capillary bridges between grains of sand, stiffening the surface and preventing the sledge from digging in. Too little water, and nothing changes. Too much, and the sand becomes a slurry that increases resistance. But at the perfect ratio, the sand becomes a smooth, solid track. This wasn't ceremonial. It was engineering, and the Egyptians understood it deeply enough to optimize it. Some sled runners even show traces of animal fat, suggesting a dual lubrication system: water to stiffen the surface, fat to reduce sliding friction. They also shaped runners with slight curvature, distributing weight more effectively. Imagine hundreds of workers pulling a multi-ton block over sand prepared with mathematical precision. This wasn't brute force. It was controlled friction and invisible technology that made the impossible manageable. And that's the thread linking these ancient breakthroughs. Whether Romans manipulating chemical reactions or Egyptians bending friction to their will, ancient engineers solved problems by studying forces we barely notice today. They didn't rely on electricity, motors, or synthetic materials. They relied on observation, experimentation, and an understanding that nature itself could be a collaborator. Roman concrete is not just a better material, it is a better philosophy, a belief that technology should endure, not expire, that structures should grow stronger, not weaker, that engineering should respect the world around it, not exploit it. And in an age where construction accounts for nearly 40% of global carbon emissions, the lesson becomes painfully clear. The future might depend on rediscovering the past. Because the Romans didn't build for profit margins or planned obsolescence. They built for eternity.